Hi everyone. We're continuing with continuous probability distributions, and we're now going to come to these bell curves. And in particular, we're going to start with our famous bell curve, the standard normal distribution, or the standard normal density curve. First of all, you might be wondering why we call these density curves. Well, here's the idea. Uh, let's say you have the state of New Jersey, right? The state of New Jersey has a much higher population density than the state of Wyoming. So, for example, if you take a square mile in the state of New Jersey, it probably has a lot more people in it than a square mile in the state of Wyoming. Well, similarly, if you look at this standard normal density curve, okay, then you can see that the probability mass is bunched up near the center, the mean, which is 0. And if you take an interval from, say, here to here, okay, versus an interval of the same width even, from, say, here to here, okay, maybe these intervals are the same width, but we have much more probability mass here near the mean than away from the mean. So we have a greater bunching up, a greater probability density near 0, the mean of the standard normal. Whereas for our old school continuous distribution, from 0 to 1, let's say, it was nice and evenly spread out. The probability mass was nice and evenly spread out between 0 and 1, or in general, from A to B. So before, we talked about these continuous uniform distributions, especially the one from 0 to 1. Now we're going to talk about this standard normal distribution. Now its parameters are also 0 and 1, but the 0 and the 1 here are not endpoints the way they were before for the continuous uniform. Here, the 0 will be the mean, and the 1 will be the standard deviation. So 0 and 1 mean something different here as opposed to here. All right, lesson 20 on the standard normal distribution, our favorite normal distribution, which tables have been written about, and we'll talk about those. What do z-scores tell us about normal distributions? All right, so there's a direct relationship between these standard normal random variates and z-scores. All right, what is the standard normal distribution? The standard normal distribution is sometimes called the z-distribution because we associate values of this standard normal distribution with z-scores in many contexts. The standard normal distribution is the normal distribution with mean 0 and standard deviation 1. So in notation, we often use z to indicate a standard normal random variate. Z has as its distribution a normal distribution with mean mu equals 0 and standard deviation sigma equals 1 unit. Remember, for the standard normal distribution, there are no specialized units like pounds or feet or yards. The idea is that we can apply the standard normal distribution in a variety of settings. We assume that z is a standard normal random variable. So when you hear about a z-score, we usually assume it comes from a standard normal, though not always. All right, so what are some properties of normal distributions in general, but especially for the standard normal? I'll bring up my copy over here. All right, so what are some properties of standard normal distributions and normal distributions in general? First of all, they are continuous. They are continuous. They can take on a continuum of values. So for example, in the standard normal, you can have values of 0, 1, 0.1, 0.11, 0.111. Any real number can be a standard normal value. They're continuous distributions. Also, a normal random variable can take on any real number as a value. Any real number is possible. The density curve is bell-shaped. It's the classic kind of bell shape, although there are others, as we'll see later in the semester. The density curve is symmetric about the mean. Okay, so we have this mean line over here, and the density curve is symmetric about that mean line. So probabilities here correspond to probabilities over here. The standard deviation is the distance between the mean line and either inflection point. I'll go to my nicer pictures down here. These are produced by Mathematica. Okay, so in general, for a general normal distribution, the mean, if you look at this center line here, the mean corresponds to this hilltop. The standard deviation, sigma, is the distance between the mean line and either inflection point. Remember that an inflection point, okay, an inflection point is where the density curve changes from concave up to concave down, or vice versa. So over here, at this inflection point, these are points you see in calculus. This is a point where the curve, the density curve, goes from going concave down to concave up in terms of the way it curves. For this inflection point, we're going from concave up to concave down. Again, one standard deviation is the distance between the mean line and either inflection point. Now, this knowledge is not absolutely essential for the homework, but it's helpful if you want to draw good pictures. Also, the tails of the curve fall off rapidly in terms of standard deviations. Remember the empirical rule. Remember the empirical rule. The empirical rule went 68, 95, 99.7%. 68% of the data, let's say, in normal data sets, 68% of the data, roughly, would be within one standard deviation of the mean. About 95% would be within two standard deviations of the mean. That would be like a usual range of values. And about 99.7%, almost everything, would be within three standard devs. Basically, you're not going to have too much too far out to the right or to the left of the mean. You're going to have a lot of density close to the mean. It's bunched up there. The probability mass is bunched up near the mean. So that was the basis for the empirical rule. The relationship between that and the empirical rule. Again, for a standard normal distribution, the picture is exactly the same, except that we know that the mean mu is 0 and the standard dev is 1. Sigma is 1. All right. So that's a review of some continuous distributions. We've discussed properties of normal distributions in general. And remember that the standard normal distribution is the normal distribution with mean 0 and standard deviation 1. No units, because we can apply this to anything, as it turns out. Next, we're going to do some actual computations with actual numbers, and we can even verify numbers like these. Oh, and before I go, in case you're curious what the equation is for this curve, this standard normal probability density curve, is this over here. F of z equals this ugly thing over here. This indicates basically a kind of exponential decay over in the right tail and the left tail. There's a sharp falling off in the tails. In general, for mean mu and standard dev sigma, here's the formula for the function. And this is the graph of y equals ya. Bear in mind, this is just a special case of this, where x equals z, the mean mu is 0, and the standard deviation sigma is 1. The bad news is it looks like these. They're pretty ugly. The good news is you won't have to know these for homework. This is mostly if you're just curious. But again, we don't care so much about the equations of these curves. We don't care so much about the y-coordinates of these points. It's not the y-coordinates we care about. We care about areas, which means that we won't need these directly. We like to use tables or software. Okay, we'll do computations and we'll discuss tables and software in greater detail next time.